Next coming up is Andrew Stine. Join me in welcoming Andrew. Still need to bring up the presentation, one moment.
Hello, I'm Andrew Stine. I'm a computational biologist at United Therapeutics, and today I'm going to be talking about a quantitative systems pharmacology model we've developed for pulmonary arterial hypertension. So first I'm going to start with what is pulmonary arterial hypertension. So pulmonary arterial hypertension is a progressive, often fatal cardiovascular disease. And basically what happens in this disease is your pulmonary arteries narrow due to several effects. The muscle cells surrounding the arteries contract, sort of narrowing the area to go through. They also proliferate, sort of further narrowing the area. And then they release compounds that stiffen the arteries, making it harder for blood to flow through. And then the net result of this is your heart has to work a lot harder to push blood through your pulmonary arteries, which puts a lot of strain in your heart. It eventually leads to heart failure and death. Sort of on the right there, you can see the overall transplant-free survival rate for patients, sort of how long they live once they're diagnosed without a lung transplant. By 10 years, more than half patients have died. So it's a very serious disease. Fortunately, there's three classes of therapies for it. There's prostacyclin analogs, which United Therapeutics produces, called treprostinil. There's also PDE5 inhibitors, and there's endothelin receptor antagonists. And don't worry, this isn't like a biochemistry talk. I'm not going to go into the details of how all these work. The important thing to keep in mind is that there's three classes of drugs, and we want a model to look at sort of how the different combinations of the drugs can work. So now a little bit on our model structure. So the PAH is sort of inherently a multi-scalar problem. All these three classes of therapies I just talked about, they all act on the cellular scale. They bind receptors, they change cell behavior, which ultimately changes disease progression. But all the clinical outcomes, the things you actually look at in a trial, happen on the organ scale or the patient scale. So these are things like pulmonary vascular resistance, which is a measure of how much resistance your pulmonary vasculature has to flow, so how hard it is to pump blood through your arteries. And also 6-minute walk distance, which is exactly what it sounds like. It's how far can someone walk in 6 minutes, which is the main outcome of a lot of these trials, actually. So we've developed a multi-scale model to try to cover this. And then because we're interested in clinical trials, not just sort of like the individual patients, we generate what's called a virtual population to simulate clinical trials for this disease. So I'm going to go through sort of each of these three parts. So first I'll start on the cellular scale model. So on the right there, we organize our cell scale model into these modules just to make it easier to work with. So if you're interested in the biochemistry, you can sort of see how all the modules interact with each other. But big picture, it's a 50-ish ODEs that we simulate for the cell scale model. And the main thing we're trying to get from it is the force of these muscle cells, their contraction, how much force we're getting from them, and how many there are, the cell number. We then feed this into our hemodynamics model that simulates sort of the organ scale, which will get us this pulmonary vascular resistance that I talked about, the resistance of flow in your arteries. And because we don't want to like model a whole person and figure out how to figure out how far they're walking in 6 minutes, that's sort of beyond the scope of the model we want to build. We went through our data and came up with a statistical relationship relating this vascular resistance to 6-minute walk distance. And then the organ scale model is a lumped parameter model. It's what's called a Wynn-Kessel model. So basically, we feed the force and the cell number from our cell scale model into a very basic material model and get resistance and compliance. And then from the patient's cardiac output and their heart rate, we can also get flow rate through the arteries. And then we create a circuit. basically, where the resistance of the arteries is a resistor, and the compliance of the arteries is a capacitor in parallel, and the flow through the arteries is the current. And when we solve this circuit, we can get the change in pressure across the arteries. And from that and the cardiac output, we can calculate this pulmonary vascular resistance, which is a key clinical outcome. And then, like I said before, from that, we can statistically estimate how far they can walk in 6 minutes. So that's great. We have a model then of like one patient, but we're not interested in one patient. We're interested in a population. We're interested in a clinical trial. So what we do is we generate what's called a virtual population. We've identified 8 key parameters that will vary between our patients. And we vary these, and we load these sort of vectors of parameters into our model and simulate it and get the results. And then we sort of have a filtering step, because sometimes you put in these parameter sets and you end up with a patient that's like an Olympic runner. And that patient isn't in a PAH trial, they're not sick. Or you might have a patient that can't move very far at all and they're too sick for a clinical trial. So we do some filtering after this, and we end up with what's called a plausible population, which is a set of these patient vectors, these parameter vectors that represent plausible patients that exist in the real world. But just because they exist doesn't mean that they're common. So the next step we do is we make what's called a virtual population, where we use something called prevalence weighting, where each of these parameter vectors is assigned a weight, which is how common it is in the population. How likely are you to see this type of patient in a PAH trial? And then we use a genetic algorithm to optimize the weights associated with each of these parameter vectors to match real clinical trial data, generating what's called a virtual population, where we have these parameter sets and we have how common they are in the PAH population. And then the last step in our process is to simulate trials. So what we do for this is we set trial parameters, such as the number of patients. So if we're looking at a trial with 220 patients, we'll set that. And then we sample, using these weights that we just calculated, we sample these parameter sets to generate that many virtual patients for a virtual trial. And then we simulate the trial to see the results. For this work, we optimize to monotherapy trials that just had one treatment. And then we're simulating published combination trials so that we can sort of validate that our model is capable of matching real trial data when you add these therapies together. So this is a JuliaCon talk. I should talk about how I use Julia. So each of these parts I just talked about uses sort of different Julia libraries. The cell scale model uses ordinary differential equations, because it's a bunch of ordinary differential equations. The organ scale model uses forward diff. And then for this virtual population generation, we fit distributions. So we use distributions.jl, we use evolutionary.jl for the genetic algorithm. And then this is the most expensive computationally part of what we do, but it's also trivial to parallelize, because each of these virtual patients doesn't care about any of the other virtual patients. So we use distributed.jl and run on Julia Hub to generate these virtual populations. We've also developed an internal Julia library called slabs.jl, which is useful for putting all our parameters and information about where they came from, the type of experiment that was used to generate them, also our initial conditions. We can put that in a Excel sheet and just load it into the model, which sounds trivial, but in our field, documentation is extremely important. If you go to the FDA, you want to be able to tell them where your parameters came from. So this has been extremely useful for us too. Okay, now I'm going to go through each of those 3 steps I talked about in the virtual population briefly. So that big graph on the right there, what we've done is we've fixed all our patient parameters, all these parameters that vary between our virtual patients, except one, endothelin 1 production. And we sort of changed that to see how that changes patient behavior. And on the y-axis, you have 6-minute walk distance, how far they can walk. And that goes down as you increase this endothelin 1 production, which makes sense. This is a compound that famously contracts your cell, causes your cells to contract, so it narrows the arteries, makes people sicker. And then on the left there, we have sort of a heat diagram of our 8 patient parameters and how they affect response with different therapies, placebo and then the 3 key therapies, I think at 12 weeks, yeah. So you can see some of these different patient parameters affect different responses for different therapies which depend on different patient parameters, which is useful. That means we can isolate subpopulations that might be better treated with different therapies. Next, we optimize these weights, like I talked about, so we fit to clinical trials. We fit to 1 treprostinil trial, which was our own. That was our data there on the left. And then we grabbed 2 trials for ERA and 2 trials for PDE5 inhibitors from literature and fit to those. We got pretty close on the median and the distribution of patients. And then we used those weights, that virtual population, to simulate combination trials. These are trials that have multiple therapies. So the one on the left is one of our trials, which was Freedom C2, where it had basically all combinations of the other therapies. You could have PDE5 alone, you could have ERA alone, you could have both of them in the background, and then we added our therapy on top. And we predicted, well, how will we do? And then that blue line on the bottom, that's the real trial. They ran the trial, that was the result. And then all the black dots with the confidence intervals, those are our virtual trials. We ran 100 of them. And as you can see, the real trial sort of fits quite comfortably in the range our virtual trial predicted. It's not an outlier. You could easily see that result in our model is still correct. The other important thing to look at for these, and what the sort of clinicians and the product development teams will look at, is these confidence intervals around the dots. Those are generated the same way they generate in the clinical trials. We treated each virtual patient as if it was a real patient, generate confidence intervals. If those confidence intervals cross 0, that means your therapy was not significant compared to placebo. Your therapy didn't work. The trial will fail. And in our results, we predicted that this trial would have failed about 80% of the time. And that blue, if you look closely at that blue, you can see the trial did fail. So that's correct. And then on the right, I show we can break this out by subgroup. We looked at different background therapies, and we were pretty good at seeing how patients do on different background therapies. So future work, I show cellular scale, always just add more biology, more pathways that are interest, more therapies. The organ scale, we want to extend that from a 0-dimensional model to a true 1-dimensional model, like I show on the right. We actually have the flow through a real tree. And we're using some high-resolution CT processing to try to get like real trees for real patients. I'd like to thank everyone I work with. This was definitely not just me. This was a whole team. And I'll take any questions.
Yes, please. Katie.
How did you implement prevalence weighting in Julia?
I mean, we ran a genetic algorithm and fit that, use that to fit. Does that answer your question? Yeah. Okay. Yeah, I've found in my experience that evolutionary algorithms are very good for prevalence weighting. I've never seen like a proof that they're effective, but that's been my like personal experience. So that's what we do.
There is a proof that genetic algorithms will work for that. The proof is bad because it just shows that it walks densely through the space. So,
oh, okay.
Yeah.
For the simulated population, did you just sample from the marginal distribution of each patient characteristic for each person, or did you have some way to like constrain the correlation structure so that you don't get like these implausible people?
So when we generated this virtual population, when we fit to the trials, we generated these weights. And those are the weights that are used for the sampling.
Oh, okay. So it's like an important sampling.
Yeah, it's like an important sampling.
Yeah, Lizzie.
For the weights, did you just do like an L2 norm to the clinical trial data and the literature data, or was that cost function more complicated?
We did, because we had, well, we did it multiple ways. I'm trying to remember what we did for this. We've done that. We've also done a KS test because we have the clinical trial data. So we have like the full distribution of the patients. I don't remember which one I showed, but we've done both.
All right, let's move on to our next speakers then. Gary and Torsten.